You ever write some code, run it once, and just go, yep, that works? Yeah, we've all been there. But here's the thing. How do you know it works every single time, for every weird input someone could possibly throw at it? Well, today, we're putting on our detective hats. We're going to figure out how we can be truly certain our code is doing what it's supposed to.
All right, so here's how we're going to crack this case. First, we'll lay out the problem. Then, we'll look at our go-to tool, testing. We'll see where it falls short, bring in the heavy hitter, logical proofs. And finally, we'll deliver the verdict on how this all plays out in the real world.
So, first things first, a correct algorithm isn't just one that doesn't crash. It's one that gives you the exact right answer for every single valid input you can imagine, and then it stops. Sounds pretty simple, right? Well, as we're about to see, proving that is a whole other story.
And that leads us right to the million-dollar question. It's something every programmer and computer scientist has to wrestle with. How do we get from, I'm pretty sure this works, to I can absolutely prove it works?
Turns out we've got two main weapons in our arsenal. On one hand, you've got empirical analysis, which, is really just a fancy way of saying testing. We run the code, we see what happens. On the other hand, there's formal reasoning, which is pure logic and math. You don't even have to run the code. One finds bugs, the other proves they don't exist in the first place.
Let's start with the one we all know and use, testing. This is our first line of attack. We're basically just going to throw some data at our algorithm and see if anything breaks.
Okay, let's take a look at a really simple algorithm. Its only job is to find the biggest number in a list. The logic seems totally solid. We'll start a variable called maxNum at -1, loop through the list, and if we find a bigger number, we update maxNum. What could possibly go wrong?
So, let's feed it our first test case, a nice, simple list of positive numbers. Okay, maxNum starts at -1, the loop sees 13, that's bigger, so maxNum is now 13. It keeps going, finds 24, that's bigger, so maxNum becomes 24. The loop finishes, it spits out 24. Perfect, it works.
Awesome, it worked. So, we're done, right? Algorithm's perfect, we can pack it up and go home, case closed. Or is it? Any good detective knows you never stop at just one piece of evidence.
And this is where our little investigation takes a very sharp turn. What happens if we try a different kind of input? This is the exact moment where testing starts to show its cracks.
Now check this out. We run a second test, but this time the list is full of negative numbers. The biggest number in that list, the correct answer, should be -4. But our algorithm gives us -1? Wait, what? Why? Well, because our starting value for maxNum was -1, and not a single number in that list was actually bigger than it. Uh-oh, we've got a bug.
And this gets to the absolute core of it. Testing is fantastic for finding flaws. It only takes one failed test to prove an algorithm is broken. But here's the catch. Even a million successful tests can't prove it's perfect. There could always be that one sneaky input you just haven't thought of yet.
So, if testing can't give us that 100% guarantee, what do we do? Well, it's time to bring in the forensics team. This is where formal reasoning steps in, and it's all about getting that absolute proof.
Formal reasoning isn't about running code at all. It's about building a rock-solid, mathematical, logical argument that proves, beyond any doubt, that the algorithm will work for every single possible input, from now until the end of time. It's like the difference between interviewing a few suspects and proving, with DNA evidence, who the culprit must be.
The best way to think about this is with the domino metaphor. Imagine a line of 1,000,000 dominoes. You don't have to push every single one to know they'll all fall. You just have to prove two things. One, that the very first domino will fall, and two, that any domino falling will always knock over the next one. If you can prove that, you've proven the whole chain reaction works.
And that's exactly how we apply it to our code. We have the same two steps. First, the base case. That's our first domino. We prove the algorithm works for the simplest possible input, like a list with just one number. Then, the inductive step, the domino effect. We assume it works for a list of some size k, and then we use that assumption to prove it has to work for a list of size k plus 1.
Now, before you start having flashbacks to your high school math class, don't worry. We are not about to dive into a bunch of complex mathematical proofs. The big idea here is just to understand the concept, that it's actually possible to build a logical fortress around an algorithm that guarantees it's correct, even if the math gets a little crazy.
So we have these two very different tools. One is practical and finds bugs. The other is super complex but gives you absolute certainty. How on earth do we decide which one to use in the real world?
Well, this table really lays it all out. Testing is easy, it's fast, and it's great at catching the most common bugs. That's why pretty much all software development relies on it. Formal reasoning, on the other hand, is really hard. It takes serious math skills. But it gives you that unbreakable guarantee, so it's saved for the really, really important stuff.
And that's really the verdict for the vast majority of code out in the world. For your favorite phone app or that video game you're playing, having tons of good tests gives us enough confidence that the code is almost certainly correct. And you know what? That's usually good enough.
But what about those times when a tiny little bug could lead to a total catastrophe? We're talking about the systems that run our cloud services, that fly our airplanes, that control medical devices. In those fields, almost certain just doesn't cut it. That's when companies will invest the time and money to get that absolute, provable correctness.
So, now that we've looked at both sides of the coin, let's end with a little challenge. It's your turn to be the detective. I'm going to show you a piece of code. Using what you've learned today, see if you can spot the hidden flaw.
Okay, here it is. This little procedure is supposed to count how many strings in a list have either an exclamation point or an ampersand. But there's a bug in there that will make it give the wrong answer a lot of the time. Take a close look. The clue is all about when the procedure decides it's finished its work. Think like a detective. What could go wrong here? Thanks for joining the investigation.